Started streaming. And announcements. All right. So it's 12:01. I am going to get started. I'm I'm confident that all of you had a chance to read this entire module over the weekend, so you have a fair amount of familiarity with all the terms already. So I'm going to conduct the lecture with that assumption in my mind. It's kind of like proof by induction, which we will touch on later. All right. So anyway, last time, I remember our last discussion or the last concept that we talked about was the needle in the haystack. Remember? Yes, I hope you at least remember that much. So the question is, if we try to use propositional logic the way that we deal with logic, we deal with Boolean algebra, then the space is infinitely large. Okay, the space of the well-formed formulae is infinitely large. So the process of proving is to start with well-formed formulae that are in the set of iota. So that's your starting point, okay? And then you can use the transformation rules or the productions in zeta to basically label more and more and more well-formed formulae as true. So now the question is, can we use these transformation rules to connect us all the way to the well-formed formula that you want to prove? Okay, that's theorem proving. Okay, and the whole idea of propositional logic, along with predicate logic, is to prove theorems. Okay, but the problem is, if you use the Boolean algebra system that we are familiar with, then it can generate an infinitely large haystack of which I'm asking you to find a needle, but I'm not even sure whether the needle is in it or not. In other words, the theorem that I want you to prove is not, I don't even know whether that is true or not, whether there's a way to connect from what is known to be true to the well-formed formula that I want you to label true. I don't even know whether there's a way. So it is equivalent to saying that I don't even know whether the needle is in the haystack or not. But since the haystack itself is infinitely large, so it is possible that you can never come back to me with a conclusion. Just because you have not found the needle yet doesn't mean that it's not in a haystack, because it's infinitely large. Do you guys understand the problem that we're having with this approach? Okay. So what we'll do instead is, okay, so here's a useful example. Okay. It's really just kind of based on what we talked about earlier. So we talked about all of this stuff already in terms of the well-formed formulae. And this is what we call the production. Okay, so let me zoom in so we can look at the production or transformation rule. So this is a transformation rule. Okay, I'm putting a blinky cursor next to it just so that we can focus on this one. So each transformation rule has two sides. Okay, it has a left-hand side, which is whatever is to the left to the t that is rotated, and whatever is to the right-hand side of the t that is rotated. Is that okay? So let's go ahead and take a look at the general format of a transformation rule. We're not going to do this for too long, okay? But we will go ahead and just take a look. So with this particular transformation rule, the left-hand side is always specifying a set, okay? Regardless of the transformation rule, the left-hand side is always specifying a set, okay? And what that set is doing at this point is it's just saying, there are two wildcards, there are two variables that you can bind well-formed formulae to. So these things are basically placeholders, okay? You can basically say, okay, I want this to match psi, and I want that to match phi. Okay, so whatever well-formed formulae that are already known to be true, you can bind those well-formed formulae to these two symbols. Are we good so far? So it's really just a way to match patterns and say, can we find these pattern matches? But in this case, there's no particular pattern. Any well-formed formula can be psi, any well-formed formula can be phi, as long as they are already known to be true. And we can start with stuff that are in the iota set. Are we good so far? So this set can be empty, as we will see later, but it can also contain a number of well-formed formulae. In this case, it's only consisting of two what we call schemata letters. So schematas are not the same as variables, because schematas are basically pattern matching symbols, and they can bind to any well-formed formula. Okay, so we'll talk a little bit about that later. This particular symbol, okay, let me move the highlight to that symbol. So we are talking about this symbol over here. It is basically just a separator, separating from what we need for the transformation to what we can transform it into. Is that okay? So this symbol, basically says infers. Okay, if you want to associate a word with the rotated T symbol, it is basically saying infers. Okay, so what is it inferring in this case? It is inferring that this expression, this well-formed formula, is also true. I think that kind of goes without saying. Okay, because what this transformation rule is saying, give me any well-formed formula that is known to be true and bind it to psi. So psi is now bound to a particular well-formed formula. It can be very simple, like 1, which is true. It can also be something that is really complex to begin with. It doesn't really matter, as long as it is known to be true at this point. Okay, and I can do the same thing with phi. Okay, find me a well-formed formula that is known to be true at this point, and I can bind that well-formed formula to phi. So the question is, can I bind both psi and phi to just 1, which is in the alpha set, and it is known to be true? The answer is absolutely. Okay, so once you have bound psi and phi to well-formed formulae that are known to be true at this point, then we are labeling this new well-formed formula to also be true. Does that make sense? If I know psi is true to begin with, if I know phi is true to begin with, don't you think phi and psi is also known to be true? And that's basically what it is. Okay, it's a pattern matching system in order to label more well-formed formulae to be true. Yes.
Did you say that psi and phi can be bound to the same well-formed?
Oh yeah, they can bind to anything as long as it is known to be true at this point. Now, once we know that the conjunction of those two is true, we can throw that back and use it for further binding of exactly the same rule. So you can see how this is potentially not very useful. Okay, we can look at another transformation rule, which is this one over here. This one is really odd because it is an empty set all the way to the left-hand side. This is an empty set. This is basically saying, I don't even need you to tell me anything that is true or not. Okay, I can know absolutely nothing at this point. Okay, but then what kind of well-formed formula is known to be true if I don't need to know anything? Grab any well-formed formula, call it phi. I can now say phi or not phi is definitely true. Right? Okay? Now, how useful is this? Sometimes it is actually useful. Okay? Sometimes we want to generate something like this out of nothing because it can be used later on. But generally speaking, it is not very useful. Does it make sense? Okay? So that means, what kind of phi are we talking about? Any well-formed formula. Doesn't even have to be true at this point. Why? Because it only says that between phi and not phi, one of them, at least one of them, is true. And that is true for any well-formed formulae in the entire system. Is that okay? So just by using this particular rule, you can label a lot of the dots, a lot of the well-formed formulae to be true, but is it really useful to label those particular well-formed formulae to be true? Generally speaking, not very much. Okay? And you can reapply this infinitely just by itself. Okay, between this one and this one, you can use these two to generate a whole lot of stuff that is actually not very helpful in the end. Are we doing okay so far? Okay. So now we work on something that is slightly more helpful. Okay, this is basically De Morgan's law. So when you look at the transformation rule that is corresponding to what we know as De Morgan's law, it is basically saying, give me just one single well-formed formula. But it cannot be any well-formed formula, because the well-formed formula that we start off with has to be something of this format. Okay? It has to be the negation of an or. We good? So that structure of the well-formed formula is now imposed. If you do not know of any well-formed formula that is of this particular form, you cannot use this transformation rule. It can only be applied if you can find me a well-formed formula that is known to be true, first requirement. Second requirement, it has to follow this structure. The last operation has to be a negation. The second last operation has to be a logical or. Now, if you can find me a well-formed formula known to be true and of this particular structure, then I can use that well-formed formula to determine what is going to be phi and what is going to be psi. It's just the two components of the or. One is called psi and then one is called phi. Are we good so far? It's a pattern matching kind of thing. Once we match the pattern, okay, then we reuse the pattern over here. And then we say, well, if this thing is known to be true, then I will tell you that this is also known to be true now, which is not phi and not psi. That is known to be De Morgan's law. Is that okay? So for every single rule or for every single axiom that we know in Boolean algebra, we can make a transformation rule for that. So now the system is going to be, it will know exactly what we know about Boolean algebra. And then in theory, if there's a theorem that is provable by us, the system would have a way to prove it as well. Are we good so far? Okay. So the last one over here is, it's kind of De Morgan's law, but it is also combining the negation thing. Combining the conjunction thing. If you know that not psi is true to begin with, not phi and not psi are true to begin with, then you can conclude that the negation of psi or phi is known to be true. Okay, so it just has a whole bunch of rules like that in a normal human equivalent propositional logic system. So when you hear the word human compatible, it seems to be good, right? That means whatever we know, we can transform that into rules into this particular system, and it's easy to read. But because of the infinite well-formed formula space, and the problem of, well, when do we stop? Okay, what if you give me a theorem that is not true to begin with, and there's no way to prove it? When do we stop? Well, we kind of have that problem. Okay, so skipping all of this stuff a little bit here. Okay, this is just an example of what the meanings can be. Okay, so well, maybe I shouldn't skip it. So what we'll say is P is a variable in alpha, and all that means is TAC is boring. It is not a statement. It doesn't say that TAC is in fact boring. TAC is boring is a Boolean variable, which means it can be true, it can be false. Are we good so far? And then we can say Q is another variable. It says, have the class falls asleep in CISP 440, which is also a variable. It is not true, it's not false, it is just a variable. It can be true or false. Okay, so we throw those two into the system and we assign meanings to those things. And I just realized that you guys are looking at a screen that is not wide enough. Okay, so let me change the projector to match what is being recorded. The recorder is already recording using this particular format, so we are good as far as the recorder is concerned. There we go. So we can actually make it slightly wider. There we go. All right. And then we have R, basically saying many students feel rejuvenated after CISP 440, after this 1 hour and 20 minutes, because those people were sleeping during this time. Okay? But once again, it is a variable. It is not a statement. It is not confirming that this is true. It is just a variable. It can be true or false. Okay? So now the question is, what can we throw into iota in addition to 1, not 0, and all the usual stuff, okay, that relates to Boolean algebra? So now we can throw into iota something like this. Okay? P is a variable, Q is a variable, right? So what we can throw into iota is to say, well, this well-known formula, this well-formed formula is known to be true. Okay? Not P or Q, which is a fancy way to say P implies Q. Okay? So what is that really saying? Well, all that it is saying is tech is boring implies half the class fall asleep in CISP 440. That implication is known to be true because it is in iota. But is tech actually boring? Well, that's a variable. Does everybody fall asleep or most people fall asleep in text class? Once again, that is a variable. So are we differentiating what is a variable and what P and Q are, what they're symbolizing? Yep.
Why is the implication true? Because the first part of it is true?
No, because it is just, I just put it into iota because, that's the known truth in this universe. Okay? So there's no particular reason, other than, it seems to make sense in this universe. Okay? So the second one, which is not Q or R, which is also the same thing as to say Q implies R, all that is saying is half the class falls asleep in CISP 440 implies many students feel rejuvenated after CISP 440. The implication itself is labeled true to begin with because it is in iota. But is Q true? Well, we don't know. Okay? Is R true? We don't know either. So now you ask, then what is the whole point of this whole thing? Because nobody actually confirmed whether tech is boring or not. Nobody actually confirmed whether many students feel rejuvenated after CISP 440. What is the whole point? What is the theorem that we want to prove? Well, maybe the theorem that I want to prove is tech is boring implies many students feel rejuvenated after CISP 440. Do you see what the theorem that I want to prove? I don't want to prove whether R itself is true or not. I just want to know whether P implies R is true as a result of P implies Q and Q implies R. Are we doing okay so far with this example? Okay? So theoretically speaking, if we build our propositional logic system with enough transformation rules and they are sound, then we should be able to prove that P implies R is actually true. Even though we don't know whether P itself is true or not, it doesn't matter because the theorem I want to prove is simply tech is boring implies many students feel rejuvenated after CISP 440. So do we have any questions about this particular example? It's the meaning of the example that is important, okay? The point that I'm trying to illustrate using this example that is important. So section 4.1 talks about completeness and soundness, okay? In other words, because the propositional logic system comprises of alpha, those are all your constants, variables, and schemata symbols. It consists of iota, well, I shouldn't say iota first, omega. Omega are your operators, okay? So you have to define your operators. And then once you have alpha and omega, then you can now define what is well-formed, because all you need are symbols, because every single symbol in alpha is known to be a well-formed formula by definition. Now, if you apply those to operators, so every operator gets enough operand in order for the operator to work, that operator expression is also a well-formed formula. So between alpha and omega, it structurally defines what a well-formed formula is. But do we know which one is true and which one is not? No, not at this point. Okay, we're just generating a space, or we're generating a haystack. What zeta does is zeta will do the transformation. Okay, it will say that if you know this to be true and that is true to begin with, then we can infer that that is also true. That's what one application of the transformation rule would do to us. Okay, but then we are still kind of hopeless because we don't know what is true to begin with. That's the job of iota. Okay, iota is a set of well-formed formulae that are known to be true. Do not ask me why those things are true. They're just true to begin with. So if we have a system like this, it is all syntactical. In other words, there's nothing related to the meaning of operators. It only has to do with, do we see this pattern? Is it matched? Yes. Okay, if that matches, then that is also labeled as true. Okay, throw the newly labeled well-formed formula into the pool, and now we can look for matches again. So this is a completely mechanical and syntactic type of operation. It has no ties to what we know about Boolean algebra. Are we good so far? So if somebody is not careful, that person can create a propositional logic system that doesn't make any sense to us. Okay, because those transformation rules do not make sense. The iota may not make sense. Okay, but we only want things that kind of are useful to us. So what we want to do is to talk about this is just a term. Okay, when we see something like this, which is what a transformation rule should look like to begin with, the symbol that looks like an inverted T, we already said that it is infers, but the other way to call this is we want to say whether it is syntactically entails psi or not. There's a different term which is called semantic entailment, and you can see that semantic entailment has about the same thing, except it has a double bar for the rotated T. So one is syntactic entailment, and the other one is semantic entailment. Semantic entailment is basically saying, if we have these psi 1 all the way to psi n, those are actual Boolean expressions. Okay, this is asking, not using a computer, not using propositional logic system, can you or a mathematician or a computer scientist prove that psi is true? If that is the case, then it has semantic entailment. So there are two types of entailment. Syntactic entailment is what the computer can do, and then semantic entailment is what the meaning of the logic really should do. Are we doing okay so far with this or not? Yep.
Does that symbol mean can you prove, or?
This means you can in fact prove it. So the double bar basically says for a human it is provable that psi follows phi 1 all the way to phi n. So if you present a bunch of Boolean expressions to a math or computer science professor and say, well, can you prove, given these are true, can you prove psi is true? And if the mathematician or the computer scientist or logician said, oh yeah, and here are the steps, okay, and therefore, okay, the last step is therefore psi is true. Well, if that is doable, regardless of the steps and how many steps it takes, or whether it takes a scenic route or not, that now has semantic entailment. Okay, so syntactic entailment is done by a computer, and then semantic entailment is done by a person. Okay. So semantic entailment, which is this one here, can also be seen as something like this for someone who wants to derive the logic. Okay, this particular symbol here, okay, this is an AND for I equals to 1 to n phi n. This should be phi I, by the way, not phi n. Let me fix it right away, because I hate it when I make a mistake, and if I leave it alone, I will usually forget to fix it. So let me fix that right away. And this is which module? 0297. And it is, here we go. Yeah, I know some people are thinking, Tech, have you ever heard of Microsoft Word or LibreOffice? No, not really. There we go. So I just fixed that subscript. Instead of n, now it is I. It is now correct. Okay. So what it really is asking is, if I know these individual phi's are true, if I take a huge conjunction of those things, does the conjunction imply psi? Because that's basically how you prove a theorem, is to have a chain of implication to the theorem that you want to prove. Is that okay? Are we good so far? Okay. So soundness means, for each transformation in zeta, we also have there's an implication going in this direction. The syntactical entailment implies the semantic entailment. Okay, what does that mean? Well, can someone remind me what is an implication? As a Boolean operator, what does it do? What is the one time when an implication is false? When the left-hand side is no. Yep, exactly. When the left-hand side is true and the right-hand side is false. So that means in order for a system to be sound, the only one thing it cannot do is there is a syntactic entailment, but there's no semantic entailment. What that means is the system can derive something that should not happen in logic. When that happens, then the system is no longer sound. Does that kind of make sense to you? Yep. Sure. Okay, so we'll go ahead and take a look at this particular implication. The left-hand side of this implication sets phi 1 to phi n syntactically entails psi, which means given a particular propositional logic system, the computer can mechanically say, hey, if these things are all true, then so is this one. Okay, it will label psi as true, syntactically, just using the mechanical method. Okay, so if this is true, okay, but the right-hand side is false. Now, what is the right-hand side saying? The right-hand side and the left-hand side are both referring to phi 1 to phi n. They're the same expressions. They're the same well-formed formulae. And psi are the same on both sides. But if the right-hand side is false, that means a mathematician, a computer scientist, a person cannot use the meaning of Boolean algebra to derive this particular proof. We cannot establish that psi is following these particular well-formed formulae. So what does it mean as a whole implication? It means that the computer says, yep, this thing is true, but the mathematician says, nope, it does not follow. It is not a theorem. So what that means is the computer system can can prove quote-unquote theorems that really are not theorems. And as a result, we label this type of problem as the system is not sound. Yep?
Would you explain it I'm thinking of the implication truth table.
Mm-hmm.
And would you explain it how, I know there's one other way that
Yep, there are 3 truths and only 1 false.
Trying to remember which one was it.
So for the 3 truths, 2 of them has to do with the left-hand side being false. If the left-hand side is false, then the implication is true to begin with. So that means in order for a system to be sound, it is entirely possible that the mechanical system cannot prove a particular theorem that a person can. It is still considered sound because the computer system is not establishing a well-formed formula as a result of something when it really is not. Now, it is incomplete in that case, okay? When the mechanical system cannot prove something that a person can, it is called incomplete because the system cannot do everything that a person can, but at least it won't give you a wrong answer of something is a theorem when it is not. Okay? So the other term, okay, I just accidentally introduced the other term. The other term says, is completeness. Okay. Now, what does completeness mean? Completeness means the opposite. Okay. So the implication goes exactly the other way. The only time a system is incomplete is this is true, which means somebody can prove something by hand. Okay. And the right-hand side is false, which means the mechanical system cannot come to the same conclusion. Then it is incomplete. Is that okay so far? So not sound means a propositional logic system can arrive at a conclusion that something is a theorem when it is not. Okay? It is called unsound. Incomplete is when the mechanical system cannot come to the conclusion that a person can. So if a person can prove a theorem, but the mechanical system cannot, then it is incomplete. So are we kind of okay with those definitions? What is sound versus what is complete? So ideally speaking, we want something that is both. Okay? Because when you have a mechanical system that is both sound and complete, that means if a person can prove something, so can the mechanical system. But the other way around is true as well. If the mechanical system can prove something, it really is true. Because we need that going both ways in order for a propositional logic system to be useful. So are we kind of okay with these terms? Yep.
What are some things that a computer would not be able to prove that a human would?
It depends on what you're missing in the transformation rules.
Okay.
So if you define the transformation rules incompletely, then there are certain derivations that the person will go like, yep, I can use De Morgan's law to do this, but the mechanical system has somebody neglected to put in the equivalent of De Morgan's law into the transformation rules, then the mechanical system cannot do it because it is missing that one piece of information that is needed. All right. So the last sentence is, it goes without saying that we want something that is both sound and complete. So are we good so far? This doesn't address the issue that we talked about last week, which is, well, we try to find a needle in a haystack that can be infinitely large, and so we cannot conclude whether the needle is not there or whether we haven't found it yet. Okay, that's the biggest problem with a propositional logic system. Yes?
So one more time for the second one.
Uh-huh.
The mechanical system
Cannot.
cannot.
Yeah, because in order for the implication to be false, okay, so let me ask you, are you talking about what makes a system incomplete?
Yeah, no, I see it now. I was just
Yeah.
clarifying whether it's incomplete if the mechanical system cannot versus just the word.
A person can, but the computer cannot.
Yeah.
Then the mechanical system is labeled as incomplete because it cannot do the same thing that a person can. Okay? But these are just terms to qualify whether a propositional logic system is good or not, okay, is desirable or not. Because if it is not complete, we don't want it. If it is not sound, we don't want it either. Okay, we want a system that is both sound and complete. Okay, so now we are digressing. Well, not digressing, but we are moving on to a seemingly different topic. It's called resolution. Okay, so resolution is an interesting step. Okay, and I propose that we can forget about all of the transformation rules except for resolution. Okay, so combining resolution with CNF or conjunctive normal form, we will transform the well-formed formula space to something that is finite. Now, if something is finite and you're asked to find a needle in a finite haystack, you can come back with a conclusion. Okay, even though the haystack may be kind of big, it is still finite. You can still search every single square, cubic inch of that space and come back with a conclusion and go like, well, I searched, but your needle is not in the haystack. You can actually come to that conclusion. Okay, but the first step is to understand what is resolution. Okay, so we'll go ahead and take a look at resolution first. We'll take a look at this proof. Okay. Now this is a proof because every single line is a true equal to, so it is actually if and only if on each line. So we start with this expression. Okay, the whole implication is an expression. I'm trying to derive what is the actual value of this expression. So this is the expression that is of interest to us, that entire thing. So when you look at it, it goes like, whoa, that's kind of awkward. Okay, so let me unselect the whole thing, and we will just go ahead and look at the expression that is of interest to us. So what it is doing is it's saying here's phi or psi, okay, as one disjunction. This is and, not psi. So these two have to match, not psi or rho. So we have three different parts to this original, for whatever is on the left-hand side of the implication. What is on the right-hand side? Well, on the right-hand side, we got phi or rho. Where's psi? Psi went away. Okay? So now the question is, what about this? What about this implication? I don't know. Let's see what we can do with it. So what did I do in the first step? Let me just kind of highlight that portion. What makes me get to this particular expression? I did not negate everything. I negate, it has to do with the definition of implication, okay? Because in implication, x implies y is really the same thing as not x or y. I just made use of that fact and I got rid of the implication. So all I did is to negate everything to the left-hand side of the implication, meaning this part here. This is all negated. So you can see how the negation ends over here. And then the right-hand side of the implication is ORed with the other part. That's just the definition of implication. Are we good so far? Yes? So if you're not convinced that x implies y is really the same thing as not x or y, you can use a truth table to prove that. Okay, so make a truth table, with x, y in two different columns, okay, and then work out every single possible way for not x or y, and you will find that the truth values of not x or y is identical to how we define implication. Okay. What about going from the first row to the second row? So I'm comparing this with what is on the second row. What did I do? What did I do in this particular step? There are actually two things that I did. One is totally trivial. The other one is not trivial, but it is still not too complicated as an operation. Yep.
You expanded out the or in the right side.
So with the or, it is I use associative in order to dissolve the parentheses. Okay, because the ordering of the or does not really matter. It's because or behaves kind of like addition in normal algebra. So it doesn't really matter how you put your parentheses when you have a chain of additions. Okay, so that's all I did. I dissolved the parentheses. What about this part here? Something got changed. I distributed the negation. That's right. So it is an application of De Morgan's law. Okay, so this is an application of De Morgan's law. So have we talked about De Morgan's law? I thought so. Yep.
That's why the sign changed, right? From
Correct. Yep. So De Morgan's law can be seen in several ways. One way to look at De Morgan's law, the way that I sometimes look at it is the distribution of negation. So instead of negating the operator, in this case, instead of negating the and, I'm now negating all the components inside the and. But by doing so, I have to change the and to a or. So I find it handy to look at it that way. Okay. So what about the second row to the third row? I just kind of cleaned up. Well, no, I didn't just clean up something, but I did something similar from the second row to the third row. In other words, when you look at this expression here, which is a negation of an or, it becomes this expression here, which means the negation is now applied to every component of the original or, but then the or operator becomes and. So once again, that's an application of De Morgan's law. So De Morgan's law is really helpful because it can basically move your negation all the way into the things that are not expressions anymore. It can move the negation all the way to the individual, in this case, phi, psi, and rho. Are we good so far? Okay. What about from the third row to the fourth row? So I'm not talking about this row to this row over here. So you look at these two rows, and then let me just kind of highlight which part we're talking about. You look at this phi, and it is now replaced by phi and 1, or phi and true. Is that really okay? It is perfectly okay, because what and is doing is something similar to multiplication in normal algebra. So what is the identity of multiplication in normal algebra? 1. Yeah, it's 1 is the identity of multiplication, because anything times 1 is whatever that original thing is. So as it turns out, true is the identity of conjunction. False is the identity of disjunction. Just like 0 is the identity of addition. Okay? So I can say something and true all day long, doesn't really change the meaning of the expression. Are we good so far? Yep, go ahead. So 1 is true in the way that I choose to use the symbols. Yep. All right. So what do I do over here? So you look at this, okay, and suddenly it becomes this. Is that really okay? I mean, psi was not even a part of this expression, and I suddenly choose to go like, yeah, we'll just go ahead and introduce psi to phi. Is that really okay? Well, the question is, do you think psi or not psi is true? Do we know that? We actually talked about it a little bit earlier today, right? Out of nothing, I can choose any well-formed formula and say, this guy, or not the negated version of this thing, that disjunction is true. I just made use of that, okay? And I did exactly the same thing with rho and true. So I introduced psi to that side as well. So what happened in the next row is just an expansion, okay? Because just like you have distribution in normal algebra, we can distribute in Boolean algebra as well. If you look at the conjunction as a multiplication and the disjunction as addition, yeah, that kind of makes sense. Is that okay? So I expanded both. I expanded, this one is now expanded into these two terms. And then this one, is now expanded into these two terms. So are we still doing okay so far with this? Okay. So you can see that Boolean algebra is a little bit awkward in certain places, like De Morgan's law. Okay, but at the same time, it's not really that unfamiliar compared to normal algebra. A lot of the usual stuff that we do in normal algebra still applies in Boolean algebra. Okay, what about the next one? The next one looks a little funky. Okay, how did I find the phi and the not phi and phi? How do I group those things together? So what I did was I find this one here, okay, and then I also find, okay, this one over here. Do you see how these two are both saying and something and not psi? So I just did a factoring, which is also something that you normally do in normal algebra. So I just did a factoring and then combine those two into one single expression. And then with this one here, I just need to find, okay, give me two expressions where they both start with psi and, okay, but the second component with one of them is rho, and the other one has not rho as the second component. So we got this one as the second component, and we got this, and then we got this one as the first component. Okay, the order of the rho and the psi is reversed, but those are the two components. So I do factoring again and put those into here. We good so far? And then we got some leftover over here. We'll deal with those later. Is that okay? All right. So what do we do next? Well, we reverse, okay, and we say not phi or phi. Oh, that's just true. Rho or not rho, that's just true too. Okay, so I simplify those back into truths. I didn't do anything with the other two. I just left those alone for now. So now you look at these two. Okay, one is saying true and not psi. Well, true and not psi is just not psi, because true and whatever is whatever. Because true is the identity of conjunction. Are we good? Okay. What about the other one? Psi and 1, or psi and true. Hey, whatever and true is just whatever. So it boils down just to psi itself. Are we good? Then we look at, hey, we got not psi or psi. That's just true, right? Are we good so far? And then at this point, I just go like, well, forget about the rest. The whole thing is true. Why? Because true or whatever is true. Once it is true, once you find one true in a disjunction, the entire disjunction is guaranteed true regardless of what else is in the or. Does that make sense? Are we good so far with this proof? What is it proving? Yep, go ahead. You mean these guys? These guys over here? If there's an and here.
No, not there. The first or, like if that was.
Okay, which row are we talking about?
Yeah, that last row. If it was one and, blah, 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 instead of one.
Oh, if this is and? Well, if it is and, that means this one and itself can be simplified out, so we cannot arrive to the conclusion of true anymore.
So you'd have to simplify it like more. You'd have to simplify it even more to if it were an.
If it were an and, then I would not be able to come to the conclusion the whole thing is true. But in this case, it just so happens that I can get to true here. So what is that telling you? Okay, I'll let you guys ignore all the steps in between. Okay, start with the original expression. Let me scroll the screen a little bit when I tie my shoes before I fall flat on my face, which cannot be recorded. As funny as it may seem. So you want to start with the first row. Okay, on the left-hand side, look at that expression, and then look at the very last row. All it says is that expression is always true. Okay, if an expression is always true, why are we interested in that expression? Because that expression is an implication. it means this implication always holds. What does that mean in return? It means if you can find me some really awkward looking expression like that, you can always conclude that this is true as a result. Let me say that one more time, okay? The one all the way at the bottom here is saying that this implication is always true. Okay, but there are three cases to make an implication always true, right? If the left-hand side is false, the implication is guaranteed true to begin with. That is not what I'm interested in. What I'm interested in is the third case of how an implication can be true, which is the left-hand side is true, the right-hand side is also true. Well, how is that helpful? Well, because what that means is if you can go through all your well-formed formulae and say, hey, Tech, I found something that looks like this, that fits into this particular format, okay? Then I can say, hey, if you can find that, okay, if you can identify the phi, the psi, and the rho that fits into this particular structure, then I can conclude right away that psi, you can ignore psi. You can focus on just phi and rho. That is resolution, okay? Resolution is this implication here. The rest of this is simply to prove to you that resolution is a valid step in logic deduction. Are we good so far? Okay? You look at this and go like, doesn't that look kind of complicated compared to some of the other transformation rules that we have seen? This one looks really kind of complicated. Okay, it has got two things. Okay, each thing is a disjunction, and then within one disjunction, it has to have one particular thing where the same thing is negated in the other one. You go like, that doesn't seem to improve things. It seems to make things even worse. So if I were to encode this into a transformation rule, now that we know that it makes sense, it would look like this. Okay, basically it means within all the well-formed formulae, okay, find two things that are known to be true. But I have a special format. I have a special requirement of which two you can locate for me. Okay, so the first one is, okay, you have to find me something that is a disjunction. Now, what can phi be? Can be a gigantic thing by itself. I don't really care. What can psi be? Can be a gigantic thing. I don't really care. I just need you to find me a well-formed formula that is or. That's it. That's the first one. But once you have locked down the first one, the second one is a little bit harder to find, because the second well-formed formula that I want you to find amongst the ones that are known to be true at this point needs to now follow this particular format. Once again, it has to be an or. Okay, that's pretty easy to find. No problem. One of the components is just named rho. It can be anything. That's pretty easy. The difficult part is the other part with or has to be the exact negation of whatever psi was in the first expression. Okay, so that makes it kind of difficult to find. Okay, but if you can find me these two well-formed formulae that are known to be true at this point, and if they fit into this particular restriction, then I can mechanically derive and label phi or rho as a well-formed formula. Is also, it can now be labeled true. Is that okay? And I claim that this is all you need. Forget about all of the other transformation rules, except for maybe switching order and stuff like that, the really trivial ones. But this is the only one that you need. What is so special about this particular transformation rule compared to the ones that we have looked at? It always keeps getting rid of stuff, right? So if each time I apply this transformation rule, it's getting rid of something, don't you think eventually there's nothing, right? It has to end at some point, because it is not expanding, it is actually contracting. Is that okay so far? So this is a nice transformation rule to have, because if this is the only transformation rule that I have, your well-formed formula space is going to be finite. It cannot expand indefinitely. Because the other one is the other rules that we had, they can expand indefinitely, easily. This one says not so. Okay? So now that we have this as our transformation rule, what are we going to do with the rest of our propositional logic system? Well, as it turns out, we have to redefine what is well-formed at this point. Okay? So I'm going to redefine stuff a little bit. Alpha is still the same as before, 0, 1, and then PQRST, those are your variables, okay? And then we have psi, we have phi, we have rho, those are your schemata, symbols. So we still have the same alpha, no problem. But omega gets a little bit interesting. Omega only needs 2 operators now. It has a negation as a unary operator, and it has an or as a binary operator. That's all we need. And somebody goes like, what about and? What about implication? What about if and only if? Those are all gone. We don't need those. Okay? But we also have to redefine, what is well-formed, okay? Because as it turns out, well-formed needs a little bit of explanation now. So is ADE is a disjunctive element, okay? That's just the abbreviation of is a disjunctive element. So we take everything in alpha and we say, if you take anything out of alpha, it is automatically a disjunctive element. Okay? It's just a label, okay? But it's not well formed anymore. It is just a disjunctive element. Are we good so far? All right? And then for each thing that is in alpha, we also say if you negate it, it is also known as a disjunctive element. Okay? So let's just say that you have 5 variables in alpha, P, Q, R, S, T. Okay? So P is a disjunctive element. Not P is also a disjunctive element. Is that okay? That's basically all the same. Are we good so far? What qualifies as a disjunctive element? It just means that something that can exist in a disjunction. Is that okay? All right? So the next one is the one that is kind of complicated. It basically says, depending on the number of symbols that you have in alpha, okay, if you know phi I, where I goes from 1 to n, and they are all disjunctive elements, okay, so all phi's are disjunctive elements, then the disjunction of those things is now a well-formed formula. It's a very restrictive definition of what is well-formed as opposed to what we had before. Okay, so I know this looks really abstract. It really is abstract. But what is the nice thing about abstraction? As opposed to showing you something by example. It is always applicable. Okay, you don't have to think about what about that, what about that, what about that, because the abstracted description handles all of those. But it does make it kind of difficult to understand. Okay, so that's why we are going to take a look at an example. Okay, so we'll go ahead and look at an alpha that has the usual suspects. Okay, false, true, P, Q, R, S, T. Okay, and then the Greek symbols, but we'll not consider those guys for the time being. So what that means is P is a disjunctive element because it is in the alpha set, right? Not P is a disjunctive element. So we can now say, okay, so the same thing applies to QRST because they are all elements inside alpha. Yep, that is true. Okay. So now the question is, what is well-formed at this point? Okay. So you go back to the definition and you go like, if I have components that are known to be disjunctive elements, then if I use an OR to connect those disjunctive elements, the OR itself is now well formed. Okay? So now let me ask you, is P well formed? Can I have a disjunctive expression that only has P by itself? The answer is yes. Okay? Why is the answer yes? Because when you go back to here, this or, this n can be 1. So it has just one term. If you only have one term, it is a disjunct. It can be seen as a disjunction expression. Are we good so far? So going back to this example, this is a well-formed formula. Okay. What about P or Q? Do you think that is a well-formed formula? In other words, is this a or expression? Yes. Does it consist only of disjunctive elements? Yes. So it is well-formed. Okay. So we say is a well-formed formula. Okay. If that is the case, what about the P and Q? Is this a well-formed formula? First question, is it a disjunction? No. Then it is not a well-formed formula. Disjunction. Okay, that's easy. What about this guy? P or the negation of Q or R. Ha! Okay, you cannot say that we got something that is not a disjunction because we got all disjunctions here. Except, okay, let's check. The overall operator is a disjunction. Okay, that's cool. But we can only have disjunctive elements on both sides of the disjunction, right? P is okay. P is a disjunctive element because by definition, anything in alpha is automatically a disjunctive element. Not a problem. What about the other side? Is that a disjunctive element? It is not. So that's why this is not well-formed. Is not a well-formed formula because the negation of Q or R is not a disjunctive element. Are we good so far?
I'm actually a little confused. How is not Q or R not a disjunctive element again?
Because that's how, okay, so how do we define what a disjunctive element can be? What can be a disjunctive element? Okay, does that help? So what can be a disjunctive element? Take anything from alpha by itself is a disjunctive element. So P, Q, R, S, T, those are all individually, they are all disjunctive elements. At the same time, you can take anything from alpha, okay, by itself and then negate it, and that is also still a disjunctive element. So not P, not Q, not R, not S, not T, those are all disjunctive elements as well. But that's about it.
So no expressions then?
No expressions, exactly. Okay. A disjunctive element cannot be an expression other than something from alpha or the negation of something from alpha. Now that is still an expression, it's just that you cannot use or and in other operators. Is that okay?
Yeah.
All right. So all that it really is saying is all the well-formed formula would look like something like this. P or Q or not S or T. That's well-formed. Is that okay? So every well-formed formula is a huge disjunction, potentially of only one term. You can have additional terms, but every single term in the disjunction can only be something from alpha or the negation of something from alpha. It cannot be another expression that has two operators. Are we good so far? Yes? Okay, all right. So getting back to here, or actually getting back to here first, okay? So now the question is, well, if every well-formed formula is like this, the question is, can we really still express all the usual Boolean expressions that we are familiar with. Well, there's one more operator that is hidden, because everything that is known to be true, they're all ended together. Okay, let me say that one more time. Every well-formed formula that are known to be true within the space, they're all ended together. They're all true at the same time. Is that okay? Yes? Okay? So that means whatever the system can express, okay, is going to be in the form of this and, P or Q or S or not T and blah, 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 blah. Okay? Everything is ended together. All the well-formed formulae are ended together implicitly. So and is never really an operator inside a well-formed formula because it is implied that all well-formed formulae known to be true are ended together. Is that okay? Sort of? Okay. So now the question is, if this is the only way for me to express Boolean stuff, okay, can we really translate everything that we know about Boolean expressions into a form like this? And by the way, this is a conjunctive normal form. This is known as a conjunctive normal form. So let's go back again and review what a CNF is. A conjunctive normal form means that you have individual smaller disjunctive expressions, and then all of those disjunctive expressions are ended together as the last operation. If you want to make a tree, okay, I'm going to use Zernal to express this. So it's under accessories, Zernal. All right, so if you were to look at an expression like a tree, which is a fairly typical way of looking at expressions. So you have a gigantic end at the top, and then each component inside the end can only be a disjunctive term. And then everything inside the disjunctive term can only be a DE or disjunctive element. So these guys can be P, Q, not R, S, and the next one can be Q, R, not S, T. This one can be Q, R, not T, okay, and forget about this branch. And then this one can be, I'm just using an example here, so it's not really particularly important what these things are. Okay? This is a CNF. How do we spell out this particular CNF? Does anyone want to try? It becomes a traversal of the tree, right? So this gigantic CNF, if you were to read it out loud, which is difficult because in English we don't have parentheses unless I say open close paren, right? So this would look like open paren, P or Q or not R or S, close paren, and Q or R or not S or T, close paren, and open paren, Q or R or not T, close paren, and open paren, Q or not Q or S or not T, close paren. That's how it would spell like. That's called a CNF. So are we getting a pretty general idea of what a CNF looks like? Okay, so now the question is, can you take any Boolean expression and turn it into a CNF? All right, so let's check it out. Okay. So completeness of CNF. Okay, so we want to look at an example. There we go. All right, so this is the original expression, okay? So the original expression definitely is not well formed under our new criteria, right? Because it has got lots of stuff. Okay, it's got negation applied to implication. I mean, and then there's a conjunction and stuff like that. So it's definitely not well formed. The question is, can I somehow transform this into a conjunctive normal form? Okay, how do we go about doing it? Okay, so this is the derivation. The derivation, okay, I'll let you guys tell me what I did with each line of the derivation. So from the first row to the second row, what did I do? What is the change between those two rows? I'm talking about this one versus the one next to it. Yep, go ahead.
I see the negation on the outside of the. I was wondering if you
This thing is gone.
Yeah, that.
So in order to get rid of that thing, I have to negate the left-hand side and then or the right-hand side, right? So R implies Q becomes not R or Q. That's the only thing that I did in that one step, okay? So the first thing I do is I get rid of all the operators that I cannot use. So implications and if and only if, those are the first thing that I get rid of first, okay? What about between the second and the third line? Between this line and the line that is next to it. De Morgan's law, okay? I distribute the negation into the or, okay? And then double negation of R is simplified to just R over here. And no other step is performed, okay? Except for the simplification, getting rid of the double negation. So starting with this, how did I end up with this? That's just distribution, exactly, okay? So basically you look at this thing as one term, and it is ended with P on one side, and then we have an OR, and then we have the same thing ended with T. So first ended with P, and then ended with T. It's distribution just like normal algebra can do. Are we good so far? Okay. And then things get a little bit out of hand, or so we think. We go from here to here. What do you think I did? Okay, mechanically it is very simple. It's just when you look at it, it looks really awful. What did I do? It's distribution again. Okay, except it's FOIL basically. Okay, it's FOIL in Boolean algebra, because I start with you can look at this as A times B times C plus D times E times F. Okay. Now, in normal arithmetics, that cannot distribute. Okay, it doesn't make sense in arithmetics. But in Boolean algebra, that distributes as well. So now we end up with what? 9 terms. Because every term in the first conjunction is paired up with every term on the other side. So you can see R got paired up, and then R not Q got paired up. RT got paired up, and then you do the same thing with the other 2 terms from the left expression. Okay, do you see how I generated this insanely long but not very interesting result? Yep.
So when foiling this, you take the middle operator of the 2 things, and that's the one that is put between the individual elements.
Yep.
Okay.
So it's the same thing that you do in normal arithmetic foiling. Because so let's check that out first. Okay, because I think there may be a question about that portion. Okay, so in normal arithmetics, this is let me emphasize normal algebra. Okay, so in normal algebra, we kind of know this is the same thing as A times C plus B times C, right? Okay, I think we should all know this, okay, because the prerequisite of this class is pre-calc, and I'm pretty sure we know this way before pre-calc. This is what in algebra 2 or even before, okay. So we know this in normal algebra, okay. Go like, well, okay, we got that, and you can see how it works, right? The last operator becomes the inner operator, the inner operator becomes the outer operator. Okay, that's how we do the distribution. Okay, so now we say in Boolean algebra, it goes kind of both ways. Okay, so I'm using, okay, let me avoid the confusion here. Okay, so I claim that this is the same thing as A and C, or B and C. You can kind of see how the disjunction kind of serves the same role as addition, and then conjunction serves the same role as multiplication. Disjunction and addition, conjunction and multiplication, they're kind of related. Okay, so this one I think most people can buy, like, yeah, we kind of get that. Okay, because you kind of get the feel of conjunction really is a little bit like multiplication. Because the only time you have a multiplication that gets a 1, when you can only have zeros and ones, is when you have 1 times 1. Okay? 0 times 1 is a 0. 1 times 0 is a 0. 0 times 0 is a 0. So it does sort of behave like multiplication. Okay? But the next one is a little bit harder to swallow, okay, which is this or C. And I claim that this is the same thing as A or C and B or C. Then it goes like, wait, this has no normal algebra equivalence. Okay, this doesn't seem to make sense. So when you encounter something that looks like this, you have a Boolean expression on the left-hand side, you have a Boolean expression on the right-hand side, and then for whatever strange reason text says they're the same, what are you going to do? Just nod your head, write it down, and say text says so, right? What do? The truth table, exactly. So you make a truth table that has 3 separate variables. Okay, so I'm going to construct a part of the truth table for you. So we have A, B, C. Okay, those are what we call independent variables. Okay, so we copy and paste the other 2 expressions because I'm too lazy to kind of retype the whole thing. Okay, get rid of the equal. Okay, and space things out a little bit so they're actually easier to read. Okay, so how many rows do we have in this particular truth table? We got 3 independent Boolean variables. Each one can be true or false, independent to the other 2. So how many rows are we talking about? 8. 2 to the power of 3 is 8. Okay, so how do we get to 8 here? Because when A is false or true, B can stay false the entire time. Okay. Oh, wait. Then what about when B is true? Well, when B is true, A can be false or true too. Right? But what about C? Well, when all of these things are happening, C can be false, right? But when all of those things are happening, C can be true as well. And now we have a truth table. Well, at least we have listed, what A, B, and C can be for each row. Okay? So the rest of this is really to look at each expression and ask, what if A, B, and C are all false? What happens to this expression? It is false. Same thing for the other expression. What happens to this expression? They're all going to be false. Okay? So you do the same thing for each row. And then what you'll find is each row will have the 2 expressions matching. They give you exactly the same value. Is that okay? Yep.
This one's a little bit easier than what we were looking at. What I was actually thinking of is when you have like this and that or that, and this or that and that, where it's maybe like a mixture of the symbols and their, like, okay, so just if you want to write it as I say.
Okay. All right. Go ahead.
So A and B, or, so like the whole thing.
In paren.
Yeah.
See how much I dislike infix notation?
Or in parentheses,
Uh-huh.
C or B.
C or
B. Yeah.
D?
B.
B?
Yeah. So is what I'm wondering, is there a general way in which these all FOIL out? So now we have multiple elements and multiple.
Okay, so this is an interesting one since you mentioned it. So with this one, you can simplify. Okay, So the way I'm going to simplify this one is to say this B doesn't even have to be here. Actually, let me double think about it. One of them doesn't have to be here. Oh, okay, I take it back. Okay, so for this particular one, I will say it doesn't even matter what A is. Throw that whole expression away and it will give you exactly the same thing. Okay?
I see that, but for fairness, let's say that can't be simplified. Could this just be foiled?
It can, well, so the foiling is you can look at, so you can dissolve the whole thing so that you can look at B, C, B or C or B as one single thing. And then you can just foil with A or B and A or C and A or B again.
A or C.
Yep.
Why can't you just get rid of the A and B?
Aha! I like that question because I was waiting for somebody to ask, why can you get rid of A and B? Okay, so this whole thing, the final operation is an OR, because you can see how the parentheses, this pair of parentheses are actually not needed, right? Okay, so we can get rid of that. And then we can say B or B, well, it's really the same thing. Oh, okay, let's put a B or B here, back here. Okay, I was mistaken. Okay, so when you have B and you also have A and B inside a big, huge OR, okay, regardless of the A, whenever B is true, A and B can be false, but since B is true, who cares about A and B? Right? When B is false, okay, then when B is false, A and B has to be false. So that means I don't really need to care about what A has to say, because B itself is going to dictate this expression in the context of an OR. So in the OR, whatever is more restrictive than one of the other expressions can be cut out, because it doesn't change the overall expression at all. So that was a good question. All right. Huh? Yeah, you can get rid of the more restrictive term. Yep.
I'll come up with a better example of what I was asking. I think it would make more sense if there was more ands.
Okay.
So for the ASL thing, I actually